Hello. In this chapter, we are going to cover circular motion. Consider an object moving in a circular path. That object has to be a rigid object. Rigid object means the object which does not change its shape or extend and throughout the motion, the distance of every point on that rigid object remains the same from the axis of rotation. So if the object is moving in a circular path, the picture would look something like this. There should be a fixed point which is the center of that circular path. If the point P has moved from this to here, then let's call this point as Q. The distance of each point P and Q should be the same from the center because it is the radius. At every point, the tendency of the object would be to go straight. So it's like you have attached a stone with a string and you are moving it in a circular path. As soon as you let go, that means the tension force is gone. The stone would go straight. It's not going to go away from it. Instead, it's going to go straight because that's where the direction of velocity is. That is called the tangential velocity or linear velocity. So at this point, it is along the tangent. And at this point, it's along the tangent at that point. So at each and every point, if I start drawing the velocities at each and every point, they will be along the tangent at that point. So every time when it goes through this change of angle, the distance covered is called the arc length. And we can write the arc length as S equal to R theta. From here, we can write S over R. We know very well S is the arc length, R is the radius, theta is the total angular displacement. So if this S is equal to R, then theta would be equal to 1 radian. This is the unit of the angle. This is what we will be using for measuring our angle. So every time when you will find angle given in terms of the degrees or any other units, maybe revolutions, you would need to convert it to radians. If this situation, we can also try to get the values for more familiar equations that we know. For theta, if S is, so theta is S over R. If it has completed one complete rotation, 2 pi R over R gets cancelled and you're going to get theta is equal to 2 pi radian. And I'm sure everybody knows that pi by 2 is equal to, pi radian is equal to 180, right? And this is equal to 360 degrees, 2 pi radians. So, we can have these set of units for angle. We can measure the angle in terms of radians. Now, if the angle is changing, for example, angle has gone from theta 2 to theta 1, final angle minus the initial angle, we can write the formula for omega average, because when the position changes, we have the velocity, linear velocity, average velocity. When the angle changes, we will have the angular velocity, which is defined as omega. Here, it is given by delta theta over delta t. The unit, since we are measuring angle in terms of radians, it's going to be radians per second. If omega remains constant, then there would not be any acceleration. But if omega changes, there would be acceleration produced, which is called angular acceleration alpha. That is given by delta omega over delta t, or we could write it as omega f minus omega I divided by delta t. The unit for acceleration is radians per second square. So see how similar it is to the linear acceleration. In linear acceleration, you have the distance unit here, which is meter per second square. Here, it has been replaced by angular displacement, because this time it's not moving in a straight line. Instead, it's moving on a curved path. Omega does have a direction. It could be clockwise and it could be counterclockwise. So if delta theta is negative number, it's going to be clockwise. Oops. If delta theta is positive number, that means angle is increasing, or angle is moving. So that means counterclockwise means it's moving in this direction. Clockwise means it's moving in the opposite direction. And we know that already when we are taking angle with respect to positive x-axis, all are going to be, if you go counterclockwise, they are going to be positive. The same applies to this. This is going to be counterclockwise. So in this situation, there is another way to find using the right hand. If I turn my finger in the direction of rotation, my thumb points towards omega. Okay, an object should be moving. In this case, it's moving counterclockwise. Omega is upward. If it is moving in the other direction, so if it is moving omega this direction, omega would be up. If it is moving clockwise, then omega should be down. Okay, but in your textbook, the direction of omega is not very crucial if you can work with the clockwise motion and counterclockwise motion and know that which one is going to be positive and which one is going to be negative. You should be good for solving the problems. We can also define the instantaneous acceleration. If delta t becomes very small, limit delta t approaches to 0, delta omega over delta t, we know that that becomes the alpha instantaneous value of angular acceleration at some instant. Just like the linear motion, in most of the cases, we will be considering alpha as a constant value. Now we are going to work with uniform circular motion. Kinematics involved in that. As I already described, the velocity at each point would be along the tangent. Sometimes it is also called tangential velocity or speed, and it is changing its direction at each and every point. Now we know that there must be velocity change involved if there is some acceleration produced. And at the same time, we know that this object is constantly accelerating towards the center, or it's being pulled towards the center by a force. So there must be some acceleration. That acceleration comes from this change in velocity. Now you could see two equations, two isosceles triangle here. One is this triangle, and the other one is using these two. I can put these two together. These are two vectors, V1 and V2 delta V. So these two triangles should go through the same angle change. Okay. So we can compare them and write the equation as delta V over V1 or just V. V1 is approximately equal to V2, or we can put them together as V equal to delta R over R. If I divide both sides by delta T, this is the displacement over time, that becomes the velocity or speed, V delta T. This becomes, my V looks like a capital V, but they all are the same V's. We can write that as delta V over delta T. I'm going to take the little v on the other side. That becomes V square over R. Now, what is this? This is change in velocity with respect to time, or rate of change of velocity, which is acceleration. This C represents the centripetal acceleration, and this is the acceleration produced when the objects are moving in a circular path. It comes from the change in the direction of velocity. However, it is possible for an object to move with a uniform speed in its motion. So V could have a constant magnitude, but its direction is changing. As a result of change in direction, it does have a centripetal acceleration, and centripetal acceleration is always directed toward the center. So if I draw a picture of a object going in a circular path around a point or a fixed axis of rotation, it's always going to be under acceleration, which is keeping it at the center. Now, where does this acceleration come from? That answer lies in the dynamics of this problem. Dynamics mean now that we are going to talk about the forces. Now, centripetal force is not a it's not like a force that we have discussed so far, like normal force or frictional force. This force is generated from other forces. For example, if I have tied a stone with a string and I am moving it in a circular path, just tension in the string is providing the necessary centripetal force to keep it on a circle. Also, if the car is negotiating a curve, then the friction between the tires and the road, that is giving the necessary centripetal force. Talking about these forces, there is another force which is a gravity force which exists between the objects. So the moon going about the earth, that must come from the gravitational force between them. So it's the gravity which is keeping them together, and it's giving the necessary centripetal force to keep it on that circular path or that orbit. So writing the equation, net forces should be equal to MAC, and M is the mass. AC, if it is the centripetal acceleration, that becomes mv square over r. This force we can represent it as Fc, and that Fc could be in any form. It could be a tension force, it could be a normal force which is giving gravitation, which can give the centripetal force and acceleration. Okay. If you look at this acceleration expression, you can see it dependence on the radius is inverse. That means if you increase the radius of the path, it would be difficult to keep it on a circular path, which sounds right, because if you have a very long string for a stone, it would be very difficult to keep it on a circle, and it's because of the lack of the centripetal force. As you increase the speed, however, it increases the centripetal acceleration more. So if you speed up the car over a curve, you are getting more acceleration towards the center. But in that case, you need to have the more friction too to keep it at the circular path, because that's what is providing the necessary centripetal force. Now, talking about the tires and the road, let's discuss an example and see how we can apply this formula to other forces. Now, for example, there is a curve and there is a car on that curve, and that car is getting some sort of force towards the center. We know that there would be other forces acting on it. It's going to be the normal force upward, because that comes from the contact. There is going to be the weight force for the car, but they should have balanced each other. The only force which remains there is the friction force, and the cars have 4 tires, so if you have to add up all the frictional forces coming from all 4 tires, that would be 4 times the friction between one tire and the road. And how much is that friction going to be? It's a static friction. Rolling friction is a static friction, and as long as the tires keep rolling, the friction would be there, and it would keep it. Since it's a curve, we can link it to the centripetal acceleration. Now, using the force, so we know that Fs is equal to mu s mg. This is a formula for the static friction. Like I already said, rolling friction is when the tire come into contact with the road, it is static. So, and this Fc should be equal to the centripetal force, because the centripetal force is coming due to friction. We can set them equal to each other. M gets cancelled, and you will have mu s equal to v square over r. So if we want to know what should be the value of static friction coefficient, for example, if the speed is 25 meters per second, how much should be the static friction coefficient in order to keep that car on track and does not slip? So mu s would be equal to 25 square divided by, let's say the radius is 500 meter. So that would give us the value of 0.13, this much. So if the static friction coefficient is not up to that value, the car won't be able to negotiate the curve effectively. Let's stop here. In our next lecture, we will work with the relationship between the linear quantities and angular quantities, and also the law of gravitation. Thank you.